Out of the ice fog of the Pleistocene epoch emerges an animal that dominated the northern hemisphere. Standing 12 feet tall at the shoulder and weighing 8 tons, the woolly mammoth dwarfs modern humans. Phylogenetically, it sits directly between the living Asian and African elephants. This close evolutionary tie means we assume they shared the same deep intelligence, complex social bonds, and sharp sensory abilities we observe in elephant herds today. The mammoth was a specialized elephant, evolved for the rigors of a frozen landscape. During the last glacial period, massive ice sheets crept south across the continents, burying temperate ecosystems and locking the globe in ice. On the mammoth steppe, the environmental baseline was lethal. Winter temperatures routinely plunged to minus 58 degrees Fahrenheit. Elephants are historically a tropical lineage. Taking a large, warm-blooded animal from that family tree and dropping it into an Arctic deep freeze presents a massive biological problem. Survival required the mammoth to adapt the standard elephant blueprint to meet the Arctic freeze. The first line of defense was a heavy thermal shield. The mammoth grew a protective skirt of coarse guard hairs that hung down as far as 70 centimeters. Beneath that outer layer sat a secondary barrier, a dense, wavy undercoat, serving to trap a pocket of warm air right against the skin. At the microscopic level, each hair follicle had its own sebaceous gland, secreting oil to coat the hair and repel water. Below the skin lay a final thermal barrier, a solid layer of subcutaneous fat, insulating the mammoth's vital organs. These composite layers effectively isolated the mammoth's core temperature from the lethal air outside. The mammoth minimized its vulnerability to frostbite by shrinking its extremities. Compared to living elephants, it had tiny ears and a shortened tail, reducing the surface area where heat could escape. The tip of its trunk evolved 2 distinct, highly mobile fingers. These allowed the mammoth to precisely pluck tiny tundra grasses from the frozen ground. Because the trunk tip was largely hairless and sensitive to the cold, some preserved specimens show evidence of a protective lateral flap, a piece of anatomy the mammoth could use to cover the tip when not feeding. This skull illustrates the extreme inward and upward curvature of the tusks. This shape effectively turned them into massive snowplows, allowing the mammoth to sweep heavy drifts away from buried vegetation. To fuel this biological engine, the mammoth featured a highly domed skull and a large, fatty shoulder hump, acting as a reservoir for energy and water during the most barren months of the year. From its trunk tip to its skeletal profile, every anatomical feature served as a functional advantage for Ice Age survival. While the vast majority of the mammoth population collapsed as the Pleistocene ended, small, isolated groups managed to hold on. On Wrangel Island, a localized population survived until 4,000 years ago. Woolly mammoths were still walking the earth while human civilization was constructing the Great Pyramid of Giza. Because these final populations died out in permafrost, they left behind mummified specimens like this calf, with soft tissue, skin, and internal organs still intact. Freezing in the permafrost meant the mammoth's genetic blueprint didn't slowly turn to stone, it remained locked in the ice. Now, modern science is taking that intact DNA and using it to build a cold-adapted proxy species. Geneticists isolate cold adaptation markers, like those for subcutaneous fat and sebaceous glands, and splice them into the Asian elephant genome. This chart tracks their projected impact on permafrost melt. By trampling snowpack, the elephants let the deep freeze penetrate, maintaining the carbon-capturing permafrost. This biological blueprint offers a living tool to restore the Arctic ecosystem, utilizing modern de-extinction to actively combat climate change.